Hello, everyone. I'm Cricket Liu. I am the Chief DNS Architect at Infoblox, and I'm here to talk to you today about DNS security, threats, and solutions. We have a lot of material to talk about today, so I'm going to go fairly quickly. I'll try to speak as clearly as I can, though. We're going to talk about DDoS attacks and their relationship to DNS, and we'll talk about a number of different things: monitoring DNS traffic, anycast, and response rate limiting, all of which are potential solutions to dealing with DDoS attacks. We'll talk about the way that malware uses DNS, and we'll look at response policy zones, a mechanism that allows you to use DNS in order to help prevent people from going to inappropriate destinations, to prevent malware from accidentally or deliberately using your DNS infrastructure. And then finally, we'll talk about dot and do, and we'll look at the various mechanisms that exist to address the challenges posed by dot and do. But let's go ahead and start with DDoS attacks and their relationship to DNS. Now, unfortunately, DDoS attacks are sort of twice the threat to DNS that they are to other technologies. And that's because DDoS attacks target DNS servers, but they also use DNS servers. And I'll talk about what that means. When I say that DDoS attacks target DNS servers, I mean that your authoritative DNS servers, the ones that basically manage your presence on the internet, are a critical resource. Without them, your customers can't reach your website. They can't just send you electronic mail. You are effectively off the internet. And unfortunately, authoritative DNS servers are very easy to find. It's impossible to hide them. They have to be publicly available. It takes one simple command, like the dig command that you see in the middle of the slide there, to give someone a list of your authoritative DNS servers. These are frequently targeted by the bad guys in DDoS attacks. NetScout saw over 10 million DDoS attacks last year, which is a 125% increase in the number of DDoS extortion attacks, and DNS was the top DDoS vector by attack count. Some of you may remember the big DDoS attack against Dyn, the DNS hosting provider, back in 2016. That was an enormous attack that peaked at about 1.2 terabits per second. Now, I said that DDoS attacks use name servers. Why? Well, because name servers, it turns out, make surprisingly good amplifiers, not, unfortunately, the kind of amplifier that you see here, which is more of a guitar amplifier, but amplifiers of traffic. So here's how that works. On this slide, along the top, we have what we call open recursive DNS servers. These are DNS servers that will accept queries from anywhere, any IP address. And the bad guy is in the lower left of the slide. The target he wants to send traffic to is in the lower right. And the way that he does this is by sending spoofed queries to these open recursive DNS servers. He's spoofing the source IP address of the target in the lower right. And when they respond not to the querier, but to the target. So he does this over and over with lots of different open recursive DNS servers, generating a large stream of queries that are being sent to the target. Now, if the responses are about the same size as the queries, well, that's not a very effective attack. So a clever attacker is going to look for a relatively small query that generates a relatively large response. And here's an example of that. Probably too difficult to read this. You can look at the slides later on, but this is a query for any type of records associated with the domain name isc.org. This is actually the Internet Systems Consortium's domain name. And these are good guys, but they happen to have a lot of data attached to that domain name. It's a 44-byte query. It elicits a 4,077 byte response. And if we do a little bit of division, that's about 93x amplification. So for every 1 byte in query sent up to an open recursive DNS server, you get 93 bytes back. That's a lot. Easy to generate a DDoS attack that way. If you imagine, for example, that you have a botnet under your control and every one of your bots has, conservatively speaking, a megabit per second connection upstream to the internet, then it can generate a 93 megabit per second stream back to a target. So every 11 bots can generate about a gigabit per second. That's a tremendous amount of traffic. There are lots of big botnets out there too. We found this out back in 2016 in that attack against Dyn, which used the Mirai botnet, which consisted of Internet of Things, IoT devices like IP CCTV cameras and digital video recorders used to record surveillance video. This had previously been used in a DDoS attack against krebsonsecurity.com, which is Brian Krebs' blog. That one had peaked at 620 gigabits per second. It had used GRE traffic. This one, however, targeted Dyne's name servers, and Dyne was a big DNS hosting provider. This attack was said to peak at about 1.2 terabits per second. And it's unclear whether the traffic was junk traffic, SYN and GRE traffic, or legitimate DNS queries. Actually, we now know that it was what we call polymorphic. So it changed form over time. And the name servers were rendered completely unresponsive for hours. Lots of high-profile Dyne customers were impacted, like the folks that you see in the lower right side of this slide. That Mirai botnet was estimated to include 1.5 million IoT devices. How? How do you get 1.5 million IoT devices in a botnet? Well, many IoT devices in the botnet shipped with a default password, and it wasn't easy to change that default password. Also, those devices needed to be on the internet because people were using them for remote surveillance. People were using them to remotely record surveillance video. So it was easy to probe them. And of course, they had to have relatively high speed connections to the internet because they were dealing with streaming video. Unfortunately, IoT devices remain a really big threat out there on the internet. It's just a problem that we have yet to solve. But let's talk a little bit about some of the solutions to this problem. What can you do? Well, you can monitor DNS traffic. That's a very, very important thing to do. Monitor the queries that your authoritative DNS servers are receiving. And you can look at aggregate query rate or top queryers. I'll show you how to do that using a couple of Infoblox products, but you can do this with any product or even with open source products if you're handy with open source graphing packages. Here we're looking at the queries received across 4 different DNS servers. You can see the graph shows that these are pretty lightly loaded DNS servers. The busiest of them is only handling about 130 queries per second. But what's important here is just that you build an understanding of what's normal for your DNS servers so that you can spot anomalies and so that you know this probably indicates that we're under attack. You can also set alerts and say, if the query rate ever spikes above a certain value, that I want to know about. That probably indicates some sort of an attack. So here we've set an alert to trigger anytime the queries per second spikes above 100,000. And finally, here we're looking at monitoring top clients. Which clients are sending us queries and how many queries are they sending? In this case, one particular IP address, 192.168.1.100, constitutes 96.6% of the queries that we're receiving. Is that a problem? We actually don't know, right? Maybe that's a proxy server or a mail server or something that legitimately should be sending us a lot of queries. But only by looking at this can we detect something anomalous. Another potential solution is authoritative diversity, using a mixed set of authoritative DNS servers. And what I mean by that is just not going all in with one provider. For folks who used Dyne, for example, well, Dyne's entire infrastructure failed during this 2016 DDoS attack. So if you were all in with Dyne, well, you lost your authoritative presence. But if you had even a few of your own DNS servers that you ran on premises, then those DNS servers were not targeted and they could continue to respond to queries. So authoritative diversity just means not putting all of your eggs in one basket, having a mixed set of your own on-prem DNS servers and hosted DNS servers. There's also a mechanism called Anycast, which is very useful in dealing with these DDoS attacks. Anycast is a configuration technique more than a technology, and it allows multiple distributed DNS servers to share a single virtual IP address. Every name server in an Anycast group advertises a route to that Anycast address to its neighbor routers, and then queries that are sent to that address are automatically routed to the closest instance of a DNS server. So here's an example of how that works. In this case, we have 2 server instances over on the right side, server instance A and server instance B. Both of them have the same IP address, 10.0.0.1, and they advertise a route to that IP address to their neighbor routers, router 2 and router 4. All of that routing information propagates leftward on the slide to router 1. And when the client on the far left sends a query to, in this case, 10.0.0.1, that's sent to its default router, router 1. Router 1 says, well, I see two different routes to 10.0.0.1, one via router 2 and one via router 3, and he's going to send that to the shorter route, right, to router 2. So it reaches server instance A responds to the client gets his answer. So the great thing here is that the client has transparently, automatically been directed to the nearer instance of 10.0.0.1. And the way that this helps to combat DDoS attacks is that from any one location on the internet, you can only see, and therefore you can only attack, a single member of an anycast group at any one time. So if you, for example, have a big botnet that's centered in China, for example, and you can generate a lot of traffic, you can only attack the individual instance in an anycast group that is topologically closest to you. If you manage to take it down, then the routes will reconverge. Then you'll be able to attack the one that's next closest, but the one that you had taken down now doesn't have any traffic going to it, so it'll pop back up. So unless you can generate simultaneously a lot of traffic from all over the internet, this makes attacking an anycast group very, very difficult. We try to make this very easy. In our product, it's all configured within the graphical user interface. But you can do this using open source software too. If you're handy with router configuration, you also need a little bit of scripting in order to tie router advertisements to your the state of your DNS server. And then finally, the last thing we'll talk about with respect to DDoS attacks is response rate limiting. This was originally a patch to Bind 9 written by Paul Vixie and Vernon Schreiber, two very bright guys who used to be affiliated with the Internet Systems Consortium. Now it's included in Bind 9 and actually a lot of other DNS servers. So here's how it works. Basically, it's a way to prevent the bad guy in the lower left from asking for the same response to be sent to the target in the lower right over and over and over again. So this is a variant of the slide that we saw earlier in the presentation. Notice that associated with the DNS server on the left, there's a token bucket. The token bucket shows a whopping 5 tokens in it. When the resolver sends a query and that elicits a response sent to the target, we look up the token bucket that is associated with the network that that target is on and the response that was sent to it. So there are lots and lots of token buckets, literally thousands of them in memory. And each one is associated with a particular response and a particular network to which responses are sent. So we remove a token from the token bucket, and then if the evil resolver sends another query, we take another token out of the token bucket. So after he's sent 5 queries in rapid succession and generated 5 responses to the target, now the token bucket is empty. And from that point, we're not going to send those responses to the target. We also fill up the token bucket again, but we fill it relatively slowly, only a couple of tokens per second. So the net effect of this is that any target only gets a couple of responses every second, at least for the same response. For normal DNS, that's perfectly fine because the target caches the response. He doesn't need to get the same answer twice a second or 100 times a second or whatever, but it does make it very, very difficult for the bad guys to swamp a target. In fact, we've deployed this on the root name servers. You can see this graph. The dashed blue line shows you when response rate limiting was implemented. And the purple traffic to the left of the dash line shows how much they were sending out in responses. By just using response rate limiting to eliminate duplicate responses, to tamp down those DDoS attacks, the inbound traffic and outbound traffic in green and purple respectively are almost the same. So now let's shift topics a little. We'll talk about malware in DNS. Unfortunately, malware has used DNS almost since the beginning of malware. Malware infects clients when people visit malicious websites. The websites themselves, of course, have names that are resolved using DNS. And then malware uses DNS in order to evade detection. It wants, when it can, to reach out and communicate with a command and control server. And it used to do that by resolving compiled in lists of domain names until it found an active command and control server. And then we realized, oh, well, we can disassemble the malware, see what's in the list, and block resolution of that list. That's easy enough to do. So then malware got smarter, and they started implementing what are called DGAs, domain generation algorithms, which are algorithms that synthesize new domain names on a temporal basis, a time-based basis. until it finds an active command and control server. And because there are literally thousands, hundreds of thousands of domain names that might be generated by a domain generation algorithm, it's very hard to block them all. Malware can also use DNS as a covert communications channel. It can tunnel data in DNS in order to communicate with a command and control server, which is difficult to detect and very, very difficult to block. The response to this is something called response policy zones. Again, a mechanism that Vernon Schreiber and Paul Vixie over at the Internet Systems Consortium came up with. There are lots of organizations out on the internet that track malicious activity. The same people who are disassembling those malware samples to find the list of compiled in command and control servers, or who are reverse engineering the domain generation algorithms. They come up with these big databases of domain names that are being used maliciously. And Paul Vixie and Vernon Schreiber said, look, right now, anybody can ask any DNS server on the internet basically anything, and it'll respond. We need to give the DNS servers a way to say, I'm going to check to see whether you're looking up something that's potentially malicious. And if you are looking up something malicious, I want to do something other than resolve it. So here's a sample RPZ. I won't go over this, but you can see it's a little bit cryptic. It looks like a regular master file in DNS, but actually these records are interpreted as policies. So the domain name on the left, when you look it up, the record tells you what to respond with. Sometimes it's NX domain, which means that domain name doesn't exist. Sometimes it's no data. Sometimes it's something else. Here's how those response policy zones work. We have on the left an infected client, a local recursive DNS server in the middle that it's configured to use, and a master DNS server over on the right that actually has a response policy zone to deliver to the recursive DNS server. So we get the RPZ data via zone transfer, the same way that we get any other zone information. And then the infected client over there on the left fires a query off to our local DNS server for a domain name, and the local recursive DNS server says, is this for something that appears in my response policy zone? Right? Is this for a malicious domain name? And if it is, he'll send an error or a redirection. He'll say that doesn't exist, or maybe this IP address, which is the IP address of a walled garden or something like that, is the IP address that you should go to. And moreover, if we find out that you're trying to look up something malicious, we'll log the fact so that somebody can come in, look up what it was that you tried to look up, see if perhaps you're infected with malware on that client, and they can do the requisite work of cleaning you up. But the great thing is that this can prevent that infected client from reaching out to the command and control server. In the case of ransomware, it might prevent the ransomware from ransoming your data. So there's a case study that I wanted to cover just briefly, WannaCryptor, which was also called WannaCry and WannaCrypt. This was based on a vulnerability in Microsoft's server message block protocols that was stolen from the U.S. National Security Agency by a group called the Shadow Brokers. Microsoft issued a patch for it very promptly after the vulnerability was stolen, but a couple months later, the bad guys released a worm that would propagate based on this. Initially, we didn't know how the infection vector was being exploited, but a young guy whose image you see in the background of this slide figured out that the malware was looking up a particular web server, the one with that domain name, the very, very long domain name that starts IUQ and ends in .com. And that domain name he saw did not exist on the internet, so he registered it. And he added an address record to that domain name pointing to a web server that was under his control. Lo and behold, it turned out that that was a kill switch that would instruct the malware not to ransom files. So we owe him a great deal of credit. And the cool thing about response policy zones, and the reason this is related to response policy zones, is that you can use response policy zones to do the same sort of thing. You can use response policy zones to answer any query any way you want to. So you can populate that domain name, for example, detect all the queries to it, respond with the IP address of one of your own web servers, and that way populate the kill switch and prevent the malware from doing its malicious work. You can get response policy zones from any number of places. Infoblox provides a lot of them. We have a bunch of threat researchers up in Tacoma, Washington, who help us generate this information, who study malware. There are other providers like Spamhaus and Serval, and commercial providers like Farsight Security, which is a company that was started by Paul Vixie and Vernon Shriver, the folks who came up with the response policy zone. We try to make it very easy to manage these response policy zones in the graphical user interface of our product. You don't have to know the underlying syntax like I showed you earlier. It's all interpreted for you. And then finally, the last thing that I'm going to talk about today is DOT and DO. DOT is DNS over TLS, DO is DNS over HTTPS. And both of these are enhancements to DNS that are designed to secure communications between stub resolvers. So, for example, the client portion of DNS that's on your smartphone or your tablet or your laptop, and the recursive DNS servers that they communicate with. We call this the last mile in DNS. Both of these protocols were designed by the Internet Engineering Task Force's DPRIVE working group, and they were intended to address the threat of pervasive surveillance and modification of DNS traffic. There are some places in the world where almost all of your DNS queries from your client devices to DNS servers are intercepted, and there are some places where the responses are modified. So DOT and DO are actually somewhat competitive. They try to solve kind of the same problems. Now there are some basic differences between DOT and DO, and I tried to show that in this slide. So DOT is on the left. It's the left stack. So it's DNS running over TLS, TLS running over TCP, TCP running over IP, of course. And then DO is DNS running on top of HTTP, running on top of TLS, running on top of TCP, running on top of IP. So DOT runs over a dedicated port, 853 TCP, right? That is unique to DOT. It makes it easy to identify and easy to block. DO, on the other hand, runs over port 443 TCP, which is the same port that's used for all HTTPS traffic, which is very hard to identify and very hard to block without also blocking regular HTTPS traffic. So there are lots of implementations of DOT and DO out there, given how recent their development has been. For example, at the OS level, Android P supports DOT. There are various DNS servers like BIND, Core DNS, Unbound, and Not that support DOT. But DO has even more implementations. At the OS level, supported in iOS 14 and later, supported in Windows 10, supported in DNS servers like Core DNS and Unbound, and also supported directly at the application level by browsers like Firefox and Chrome. The way that DO is supported has changed somewhat. There are two real models to supporting DO. One is what I call the Google Chrome model, where Chrome looks at the resolver configuration on the computer or on the device on which it's running, and it looks for an IP address that it recognizes, like 8.8.8.8 or 8.8.4.4, which, if you don't recognize them, are Google public DNS's IP addresses. And if it sees those, it'll say, I know that Google public DNS also supports DO, so I'm just going to use the DO version of Google public DNS instead. So it's trying to infer the desires of the administrator. Now, the Firefox model is different. The Firefox model just says, I don't care what's in the system resolver settings. I'm going to ignore that and say, I'm going to use these other DO servers. And it does give you a little pop-up, and it says, hey, I'm going to give you more secure encrypted DNS lookups. OK. And if you click OK, it completely ignores the system resolver settings and uses what Firefox calls a trusted recursive resolver instead. And the big trusted recursive resolver is a US corporation called Cloudflare. And then there's Apple. Apple does a whole bunch of different stuff. They have a system where the way they select a DNS server is the sort of ordered list that you see on this slide. If there's a captive portal test zone, it'll use the DNS server for that. If you have a VPN or DNS proxy configuration that's set using mobile data management, it'll use that next. If not that, then If you, as the owner of the device, have configured a system-wide encrypted DNS server, that is a dot or a DO server yourself, it'll use that. If not that, it'll use an encrypted DNS server designated by domain owner. What that means is that I, as the administrator of nxdomain.com, I can say, I want you to use my DO server to resolve nxdomain.com domain names. And then number 5, encrypted DNS servers designated by individual applications. So if I'm an app publisher, I can say, if you're using my app, you should use this DNS server, right? Rather than whatever your default is. And then finally, the lowest precedence here, unencrypted DNS servers that might be specified through DHCP options or router advertisements. The sort of things that you as an administrator are actually telling your users to use are the lowest in the hierarchy. It's kind of crazy. Imagine a world in which every app on an iOS device might use a different DNS server. That's nuts. So the reason that this matters, the reason that it should be important to you is because this allows your clients to bypass your DNS infrastructure. You cannot prevent them from accidentally or deliberately visiting malicious domain names. You can't determine what they've resolved for troubleshooting purposes or to understand how bad a particular breach has been. And you're potentially sending information that is sensitive and valuable to an organization that you may have no contractual relationship with, like Cloudflare. If you're in Latin America, for example, maybe you don't want to send all this query information to Cloudflare, which is a US-based company. You also, of course, can't provide your users with any kind of SLA, because how do you know? How do you know how long it's going to take Cloudflare to answer a query? So there are a number of things that you can do here. For DOT, you can block traffic to port 853 TCP. For DO, you can deploy an RPZ. We offer one at Infoblox that prevents the resolution of DO URLs. Firefox uses a canary domain, which is a particular domain name. And if you have an RPZ set to resolve that a certain way, it'll prevent Firefox from using DO. And finally, you can block traffic to IP addresses that are known to offer DO. So that's what I have for you today. I hope you guys enjoyed the presentation, and hope to talk to you in person at the next event. Bye-bye.